Oh, it's 12 o'clock. Okay. Hi, everybody. We'll get started right on time and welcome to this sponsor session about Microsoft MakeCode. I am Tom Ball and I'm joined by two other members of the MakeCode team, Feli and Mihao. They'll introduce themselves when it's their turn in this presentation. Microsoft MakeCode, if you don't know, is a 4-year-old project for learning how to code. And it's a result of Microsoft research. A number of people here, a couple of our colleagues from Cambridge, James Devine, Steve Hodges, as well as a whole set of people in developer division. Those are the people who bring you things like TypeScript, Visual Studio, VS Code, and all the tooling. So we have a whole set of people over there that we work with, and that's the MakeCode team. If you're interested in papers about the technology you hear today, there's a link at the bottom here. You can just search for MakeCode Microsoft Research and get to the homepage that we have on the research site that has pointers to our publications. So I wanted to give you sort of the idea behind MakeCode. It started out of a project we did with the BBC. And the BBC had designed this cool little board called the Microbit, which is our Arduino style board. These boards are usually programmed, shown at the bottom. They're based on microcontroller technology. They're usually programmed in C or C++. They have very little RAM. The Microbit here has 16K of RAM. You generally use things like the Arduino IDE or a professional integrated development environment. And our idea, coming from sort of the web side, was, well, the world of frameworks for beginning programming like Blockly and the goodness of web apps and TypeScript is this whole world we occupy. Can we do something to bridge the gap between the world of the microcontroller, which typically you program in C, and the world of the web? And so one way to think of Microsoft MakeCode is bridging that gap. We're using web technology and compiler and programming language technology to bring the worlds of the web and the microcontroller, or the MCU, the microcontroller unit, together, and primarily focused on educating, helping students and teachers and parents who want to learn more about computing via these physical computers that you can wire things to sensors and actuators. So that's MakeCode in a nutshell. And over the years, we've created a platform essentially to host different editors, or different targets, we call them, for different types of boards. So we have the Microbit, which is actually done by the Microbit Education Foundation, and they have a website and an editor, and we provide the editor for them that includes Blockly and JavaScript. It's based on some cool subset of TypeScript. TypeScript is a gradually typed version of JavaScript. We've defined a subset of that TypeScript that we can compile effectively onto a variety of different boards with as little as 16K of RAM in the case of the Microbit. So MakeCode is a web app. You get it in your browser. It allows you to program against this hardware in a simulator, as you'll see, but there's also a compiler down to machine language, actually assembly, home assembly, in the web browser, and linking against the precompiled image of the C++ runtime that comes from Lancaster University. So in addition to the square board, as we call it, we're a platform. We've gone to the round board. That's the Adafruit Circuit Playground Express. We even have an editor for Arduino style boards that require wiring. So that's MakeCode. In a nutshell. You'll get, most of this talk is going to be a demo. The sort of highlights are the web app for an end-to-end experience, including editing, simulating, testing, and debugging, as well as compiling to bare metal. The in-browser compilation. Everything we do is open source. You'll hear more about that later. We make use of great web frameworks like Blockly, so you can do this drag and drop programming that you'll see. At the core of our language is really everything is in order to go to both the web browser and down to bare metal. We define the static TypeScript subset of TypeScript. So this is a full object-oriented language, but without all the dynamic binding and that you might find in JavaScript. Michał will tell you more about that. And then we have runtime extractions written in C++ at the low level. We have a little operating system that has coroutines and a message bus. This was done by James Devine and his professor advisor at Lancaster University. It's called CODAL. And then we have lots of cool technology to do mapping, a foreign function interface between C++ and static TypeScript. We have ways of annotating APIs in TypeScript so that we automatically get blocks. And you'll get to see a bit of that as well. So there's a lot of interesting compiler technology to go back and forth between these different languages and to provide the end-to-end experience. Today we actually have 6 main targets. There's the microbit in the upper left, Circuit Playground Express. These are sort of the Arduino style boards, but with some sensors and lights built in. There's a very popular version of MakeCode for Minecraft, so that's more in the gaming simulation arena with Minecraft Education Edition. There are 2 robots that can be programmed with MakeCode. But what we're going to focus on today and tell you more about is Arcade. So in the case of all the other 5 targets are editors, we partner with somebody else who provides, the hardware, the robot, or say in the case of Minecraft, the gaming environment. We wanted with Arcade to go in a different direction and to define our own sort of hardware spec for a gaming handheld. And that's what Arcade is. So it's a browser-based retro game development, execution, and debugging environment built with MakeCode. The entire game engine is written in static TypeScript, so it's probably the largest example we have. And whereas a lot of the microbit code is, the runtime is in C++, here the entire game engine is actually written up in static TypeScript, and there's various compiler optimizations we do to make it efficient to get good performance in the game engine. There's a reference design for the hardware, so that anybody who builds hardware that meets that spec, we will not just be able to simulate in the browser, but compile down to hardware. And we can compile to a variety of devices. So with that, I'm gonna hand it over to Pelle. He's gonna do a demo. Maybe I should stop just if there are any questions. That's just a high level overview, but Pelle will take over and do a demo if there aren't any questions.
You have to stop sharing.
Okay, there you go.
There you go. Thank you. All right. Well, thank you, Tom, for this intro. Hello, everyone. My name is Pelle. I work with Tom and Michał here in MSR, and I will be showing you MakeCode and how it's being used by kids. So here we are in the browser. Here I have this frame here is arcade.makecode.com, and this is kind of the typical layout we have in MakeCode, which is for the learners using Blockly. Blockly is the library by Google that allows to build visual programming languages. So in this case, I've started a little piece of game, and you can see it's running in the simulator on the left. So this piece of blocks, which is Blockly, gets compiled to JavaScript, which is static TypeScript. And then this gets compiled to either JavaScript to run in the browser, which we see here, or if I click on download, it'll get built for our ARM thumb assembly and so forth. All right, but let's make some changes. So what I'm going to do is change the duck, and this is really, if you think about getting students excited about coding, definitely give them a pixel editor because they really love that. I'm going to make my duck a bit more radioactive here, put in some little dots here, let's make it more exciting. So we've got a full pixel editor in there, and you can see that he's in the backdrop is not great. How about a blue backdrop? So we have a recompilation that happens in the background, and then you can see that the game happens. In this case, it's bouncing on the wall. So we have 2D arcade physics that are written in static TypeScript. We'll take a look at that. What I'm going to do is I'm going to have my instead of moving randomly, I'm going to go and control that with the buttons, and you can see that now I'm actually running this, which is great. And I'm also going to add an event to shoot some projectiles. All right. Now I'm really coding in blocks here. No, I don't want that. I want this. But maybe I want to switch to JavaScript. And we're going to be shooting pizzas or no, apples. Okay, so what does it look like now? Now when it restarts, I'm shooting apples kind of randomly. So we've got a nice little game engine here. The game is working in the browser. We can also play full screen if we want to kind of figure out what's going on. But all I'm going to do is, before going to the JavaScript, I'm going to go to the hardware and show how this looks like. So let's go and show. We've got a camera here, and we've got a beautiful little piece of hardware, which is the MeowBit. And you can see that it's a fairly small device. You know, if you compare it to the microbit, it is the same size. It's half the size of a credit card. And it's got your 4 buttons and A, B. So very similar to what you were seeing in the browser. So now going back to the browser, what I'm going to do is I am going to click on download. And this will let me select the different hardware. So we've got a number of different possible hardware, and MeowBit is one of them. So I'm going to click on that. And now we're compiling for this chip, which is an STM32F401, if I'm correct. And what we're going to do is going to drag and drop this file. So you're not seeing that this is a menu on my machine, but I'm doing a drag and drop onto a drive called Arcade F4. And you can see that there's a little light blinking here. And now I have my game running on my hardware. In fact, I'm just going to unplug it. It's now flashed, just like in the 80s. The game is now following you on the hardware, and you don't have to, you can put it in your pocket, and you can go and play, no problem. The game is just there in your pocket. It's right there. So that's really something that's kind of novel and unique with Arcade. We have this close relationship with the hardware, and we can take some very basic blocks game and then take them into some very constrained hardware to run the code. And Michael will have more details about how constrained this is. I'm going to drill down a bit into the JavaScript. Now let's go and hide this. So this is what the code looks like when you're doing JavaScript. And you can see that we're using the Monaco editor. So we've got a few of the goodies from Monaco here, like collapsing. You can see how the images are stored as little bitmaps of hexadecimal values, because we only have 16 colors in our palette. So we can kind of poke around the duck. I think that's the apple. Yeah, I'm going to do some dots in the apple here, and there are idioms you can see here. This looks pretty much like what you would write if you were writing TypeScript, or even, yeah, it's more like TypeScript than JavaScript at this point, because you can see that these are objects that are located into a namespace. What's also possible, if you're interested to drill into the system, is to go and look at all the libraries that have been loaded in this game. So in this case, for example, if we look at the game library and we go into something like Hitbox, we'll see that we actually have classes, constructors, we have property getters, and so forth. So there is object orientation that is supported in the static Python, static TypeScript language. Whoops. Now, one more thing that's interesting, if I drill down all the way down here at the bottom, and I'm going to go and put a little arrow there, right there, you've got your build outputs. And the build outputs are cool because you can see, what it looks like in the, so this is the JavaScript that the browser runs. And it is not really friendly. It is continuation passing style, not something you'd want to go and step through. And it's really, it's very similar to this version here, which is the assembly code that then gets run on the hardware. So it's interesting that you can actually go as deep as very close to the metal, although you're kind of in an environment that started with blocks. So that's a quick overview of the arcade ecosystem. I'm gonna tweak a bit the program just to show the editing experience here. So what are we gonna do?
Oh, hey, Pelly, one thing I want minute. Are we going to show how we get from TypeScript up to Blockly? You showed sort of the path down.
Yeah.
Okay.
I'm going to modify it. So that's a great it's a great segue, Tom. Thank you. So what I'm going to do here is I'm going to add an event that triggers every 500 milliseconds. And I am going to just do something like, I'm going to create a projectile from the side. You can see that this is the beta of Arcade. So we have little bugs here of completion that working on. We have a string literal. No, it's not a string literal. We have a function here. It's a literal that we use to compile. So that's going to be my projectile. I'm going to do some kind of scary arrow. There we go. And it is going to come from, it's going to come horizontally. So that's my speed Vx, and Vy is going to be vertically. So I've made changes in TypeScript. You can see that this is not great. So I'm going to do, my screen is 120 high. So I'm going to get that kind of randomly on the screen. Okay. And it's not so much what I wanted. I think I wanted my velocity. So we're getting there. So I'm going to do something like that. All right. So if you're familiar with coding, I should probably store that in a variable. And then call this projectile. So you've got all the things you're used to in a IDE, squiggles. We've got this new error list now showing up. So you can kind of review everything that's wrong. So a very nice coding experience for the people learning to make the game. And now I've got kind of a weird game going on. All right, so Tom wanted to go back to the blocks. And this is the moment of truth. And we're back to the blocks. So what we did was decompile the TypeScript and map it back to blocks. And you can see that this particular block here, this one here is new. So this wasn't there. And, yoo-hoo, we got blocks.
Hey, Pelly, the other thing I was thinking about was how we annotate the TypeScript APIs so we get the blocks automatically. So you don't need to know about Blockly. That was the other
yeah, that's a great topic. So for example, where is this block coming from? When you think about on game update, you're kind of wondering, all right. So if you go to, the way you would figure that out is if you go to JavaScript, you figure out, okay, this is a TypeScript that represents the blocks. And what happens in MakeCode is every block is mapped to a TypeScript function or property. And then that TypeScript function is going to be annotated with information about how to be rendered as blocks. So if I go here, it's probably going to be in game somewhere. And now I can search, probably I can search for update. On update interval. All right, so we found it. This is our function. And you can see that we use the information, the type signature that TypeScript gives us. So it takes a function here. So it is a handler. So we need the mouth block. And it also takes the period, the interval. And then also, very importantly, we have here the natural language description of how you would render this block in blocks. And most importantly, this is also translated in more than 30 languages now, so that kids who don't speak English can also learn to code. So when you're in blocks in particular, and you're a non-English speaker, we're going to render those blocks in a different language, in whatever language you're using. So that's an overview. Did I miss anything else, Tom?
No, that's cool. Thanks, Pelly.
All right. So I'm going to
do we have any? Let's see if we have any questions from the audience. Nothing in the chat.
Yeah, so all this stuff is live. If you want to try it out, it's arcade.makecode.com. And I'm going to give my sharing to Michael.
But do you want to show the GitHub or integration?
Oh, yeah.
Oh, yeah. Give it.
All right, so I forgot that detail. Okay, so one, the way kids typically share in school environment when they don't do a login is that you can basically take a screenshot and publish, and this is an anonymous publishing. You get a link, that's a deep link to your project, it's secret, and you could store that, but you kind of lose those links. So we did a bunch of work to help with bringing the experience of GitHub in the editor, and you can see that we have this new wonderful button here that lets students create a repo out of a project. So I'm going to go ahead, and it didn't accept my token because it's probably, ooh. All right, so there's probably going to be, oh yeah. No, I can't, okay, I'm going to have to switch to, your real browser. So you're going to lose, you still have my voice, but you're going to lose my my video because GitHub doesn't accept to, I guess it's boxing out the iframe. All right, so I'm going to sign in. Oh my God. You know what, Michael? Do your demo, and then I will.
We'll come back to GitHub.
I will come back again.
Okay.
Good two-factor.
Yeah.
Very secure.
It's very secure.
Nice.
It's very secure. Yeah.
Okay, thanks. So stop sharing.
Yeah, I'm stopping to share. There you go.
Okay. No, wait. I need to do that. And can you see my slides?
Yes.
Okay.
Yes.
So what Paddy has been showing you is like what the user sees. And I'm going to tell you just a little bit about what we did to make that happen. And essentially what we're after is this programming environment that can be easily deployed in schools. And what happens in schools is that the internet connections are spotty. It's really difficult to install anything. There are those paranoid IT admins blocking and everything. So essentially what we needed to do here is to have a solution for programming those embedded devices that run in a web browser and that didn't, tax the internet connection too much. So essentially, there is like a few technical challenges here. One is how do you send the code from the that is compiled to the device, and the way we do it is by having the device expose itself as a USB mass storage device, and this is something that was done by Embed before. We have developed a different file format that is optimized for that use case. It aligns with the way the USB protocol, the USB mass storage protocol works. And that makes it simpler to write bootloaders for those small devices that accept the files generated by the web browser. The other challenge here, so one challenge is this, like the fact that we have to run the web browser. The other one is that we have to deploy to the device. And finally, there is very little memory on those devices. They are actually reasonably fast, anyway, compared to the device from the 80s or so that those games were running on, for example. But they have very little memory. And for example, on the microbit, it's often as little as 2 kilobytes of memory. And because of that, the microbit itself has 16 kilobytes, but if you try to run Bluetooth, you kind of end up with maybe 2. And that makes it really hard for interpreters to run on those devices because they usually want to construct the abstract syntax tree in memory and so forth, and you just don't have memory to do that. And of course, you can't even think about running a full-scale JIT on something like the microbit. So the solution that we came up with is this language called static TypeScript, which is a subset of TypeScript. TypeScript itself is a superset of JavaScript. It essentially adds optional type annotations. And the most important changes that we have made, or restrictions, is removal of eval and prototype inheritance. So instead of prototype inheritance, we have classes. which are somewhat easier to compile and tend to use less memory. We still have garbage collection, exceptions, the any type, so the full of dynamic typing, optional dynamic typing. And it's static in the sense that there is no eval and there is no prototype inheritance, so you kind of can't mess up with the you can do monkey patching and so forth. So in that sense, the control flow is static. And the main target for that language is 32-bit microcontrollers, especially ARM Cortex-M. And this is the most popular. ARM Cortex-M has the most popular microcontrollers, and there is literally like 10 billion of them shipping every year. And we look at the devices between like 16 kilobytes of RAM and a quarter megabyte of RAM. When we compile it, we actually get quite decent performance. Sometimes it gets in the ballpark of V8, but always it's like at least 10 times faster than interpreters that are often used on those devices. And you've already seen the link, there will be more links. It's like all open source compiler and assembler and so forth. So the compiler architecture is fairly standard. We use the TypeScript compiler, which is already written in TypeScript, already runs in the browser to generate the ASTs. Then we run 2 passes on that AST, emitting in some intermediate representation, custom intermediate representation. And then we transform it into either the continuation passing style JavaScript for running the simulator. This is what Paddy was showing you. Or ARM thumb machine code. We also have a custom VM that achieves more code compression, but the main reason for that VM was to run on operating systems that don't let you generate code on the fly, like for example iPhone or Xbox. Yeah, and for those emitters that are not JavaScript, we have a built-in assembler that then generates machine code in the appropriate format. And that machine code is then linked with the precompiled C++ runtime. So it's essentially just appended at the end. And then we have to like patch it in a few places so that the runtime knows where to look for the code to execute. But the machine code has direct links to the functions in the runtime, and the runtime essentially has one link into the code to just start it. And when you actually write those functions, those runtime functions, it's the compiler that takes care of the gluing code, which makes those functions reasonably easy to write and read. So the functions will take typical C types like int and so forth, and the compiler takes care of transforming our internal representations to ints and other C types. And how does this runtime look like? So the classes are laid out like in Java or C# with just the tables. It's a single inheritance. There is some additional, there is a bit more metadata in there to make sure that the name lookups are quick, because in JavaScript sometimes you don't know what the type of the object is, and you still want to access a property by name, and you want to be able to look it up reasonably quickly. In JavaScript, all numbers are doubles, pretty much, when you use them, but you don't really want to use doubles all the time on those machines because they have no floating point coprocessors. So instead, usually we use 31-bit tagged integers, and if you overflow or if you have a fractional value, then we go to boxed doubles. Strings, I mean, we have actually Unicode in there, and even things like const strings or loops for constant time string concatenation. Yeah, we also have a garbage collector, And actually, before we were using ref counting, and it turned out that these garbage collectors was significantly faster because of the way that we compiled the ref counting, essentially. Because compiling them, I guess, much smarter would require quite a bit more static analysis. So in the end, it turned out that GC was much faster. There are some performance results here. So we ran a few tests, and I mean the main kind of takeaway here is that this is just a simple benchmark that just creates a binary tree and works over it. And the main thing to see here is that that the static TypeScript here is comparable to Node.js, and it's significantly faster, more than 10 times faster than the embedded interpreters like Ducktape, IoTJS, or MicroPython. We also compared against ourselves, against the virtual machine, and the virtual machine is typically about 5 times slower than the natively compiled static TypeScript, which essentially just tells you that so if you compare this number, 11 times slower than C, with the 40 times slower than C for MicroPython, that's the difference in our runtime systems. And the five times between static TypeScript VM and static TypeScript native is essentially the effect of the compilation to native code. So the interpreters are slower also because they represent the classes differently. So like every object is essentially represented as a dynamic map, and that takes quite a bit of time and memory. And typically we are not that close to Node.js, but the comparison with the interpreters is quite similar, and the 5x ratio here holds. This is essentially a benchmark that just goes over an array and swaps elements in an array. So very kind of low-level C-like thing. And V8 is actually quite good at those. It's almost as good as C. This one we thought was kind of more representative. It's a benchmark that moves elements between lists that's meant to represent tasks in an operating system. And here we are actually kind of in the same ballpark as V8. And again, tens of times faster than the interpreters. Okay, so here are some links to check out, and I guess we can like paste them in the chat or something. And are there any questions to any of us?
Yeah, we can take questions now. We can also go back to Peli for looking at GitHub. But let's take a break. Just you can unmute and ask your question, or you can type in the chat, whatever you like. Let's just take a break first. See if there are any questions about what people have seen so far. Okay, well, we'll go on in that case.
No, I think there's a question.
Oh, I'm sorry, where? Will.
Yeah, hey.
Hey.
Now?
Yeah, go ahead.
We can hear you now.
I'm wondering are you guys using LLVM for the backend or writing your own loader for that, for the thumb and whatnot?
No, this is all written by hand by Michał primarily. It's all written in TypeScript. In the web browser, we compile from the TypeScript AST to an intermediate representation. And from there, we have different backends, all written in TypeScript. One to thumb assembler, and then we have a thumb assembler, also written in TypeScript, to machine code. So part of the idea here is like we didn't want to have to, like we want to deliver a web app into the web browser in the school setting and have no dependencies on any other tools or need to do anything fancy like taking a big C compiler and shoving it into a web app. So for our viewpoint, we have a fairly restricted language, but it was really key, especially for the success of the microbit in schools, that we not have dependencies on external web services to deliver a compiler service to us. We tried that, it was flaky, or to require IT admins to install a tool set or a tool chain. Yeah.
And also with things like, Mscripten and so forth, I mean, I imagine that if you compile GCC with mscript, you get, tens of megabytes. So this is something that we also wanted to avoid.
How do we have it? Sorry.
Yeah, everything I said about VM, it actually doesn't really, we don't really use it. It was mostly to like benchmark, and we had some ideas for it, but we never ended up using it. So it's all really native. Yeah.
We have another question from Gabor about debugging, profiling, and similar tools. So maybe Peli, you can also show the debugger.
Yeah,
and
I can show
Mihao, you might talk about the profiler later. So yes, we do have debugging.
So yeah, if you look at it's related to the simulator. So whoops, that was the wrong side of the arrow. But let's do that again. There's this little icon here. So we're working on a debugger and working both on an experience for blocks. So you can see that here there's some little dots here. Oh, okay, they're red now, but here. So these are a way to put breakpoints on your script. So for example, I'll put a breakpoint here, and then whenever my code execution hits that breakpoint as expected, we hit there. So we're in blocks land here. There's a very few options you can do. You can step, so you can do step by step. You can keep going, or you can also turn on tracing. That means we're running the steps slowly, one by one, and then we're going to break again here. There's a variable table where you can drill into objects or variables and look at what they're doing. So it's really a debugging experience that we all know, but mapped, simplified for blocks. If you then move to JavaScript, you actually have a bit more things that you would expect. So let me put a breakpoint around here. When we break here, you've got step over, step into, step out of, and also we have a call stack. So yes, there is and this is a debugging experience that runs in the browser. We don't have yet a hardware debugging experience. It adds a lot of technical complexity to reliably connect to the hardware and talk to it, although it could be possible in the future. Yeah. A long answer.
Peli, could we let Mihao talk a little bit about profiling? Profiling is more for developers, not for the end users, right? Although we do have the ability to do the graphing, which is interesting. I'll let you guys go.
Graphing. Yeah, so profiling, I mean, we have some ways of profiling in the browser, and it's essentially just, there's a bunch of performance counters. You can add your own performance counters and just have them, dumped every couple of seconds. You can do the same thing for tracking memory usage in the simulator, and that also has a way of showing the objects that are live that came since the last dump. They were present in the last two dumps, but not before. So essentially, you can detect memory leaks that way. But it's not very user friendly right now. It essentially puts stuff in the console. I mean, it's not as user friendly as the rest of MakeCode, maybe, to put it that way. On hardware, we can do the memory, we can do the profile, the timers, the performance counters, and we can, if you connect via USB, you can dump them. But I think that also right now only works from command line. So there is some profiling, but it's not very advanced.
It's meant for Michal and the MakeCode team.
Yeah.
And I think that's how you call them, right, Michal? There's heap dump, there's GC stats.
Yeah.
But sometimes one of the things that I did was I put in some counters in like one of my programs, and then I outputted it to the console, and then I could see like how many objects of certain types were coming through in the graph visualization that we have built in. So you can actually, that's sort of a cool way to do things.
Oh, right.
Really sort of low tech, but maybe you're going to show something like that, Peli. Yeah.
It's going to be too slow. I'm going to do another loop here, but keep going.
Yeah. So in a lot of MakeCode, we have the ability to read sensor values like accelerometer and from devices, and so we can pipe that over serial back to the web browser and graph it. Of course, if we're running in the simulator, we can also just take the simulator values our program internal state. And so if you add some counters, you can then easily create a little graph by outputting to the log, and then we have some automated graphing that will happen. So you see the simulator, and then well, we're not getting a graph because you're not using log value or something.
Yeah.
Right. Yeah.
There's some format to it.
Okay. So maybe this demo won't go great. Let's see. Oh, there we go. There we go. Super. Yeah. So actually, I found this super useful when so just doing some very basic profiling and to show students, hey, you can collect some values and then you can graph them and just get an idea. And that's in some sense, I think, a nice way to learn profiling. Instrument it yourself. You collect some counters and graph them and just see what's happening. Yeah. Thanks, Pele.
I was about to get the acceleration out of the system.
That's all right.
But yeah, we only used to have the log until we recently added the debugger.
Oh, Pele, can you do something for me? Can you type class foo left? Can you write a class? And because we have a question, and then go back to blocks. So what happens if the JavaScript side code does not have corresponding blocks?
Oh, yeah.
So as much as possible, we attempt to convert whatever program you type back to blocks, but we don't have a block for every syntactic representation. What's going on there?
The blocks are going to be unhappy.
No. We should get a gray block. It should work, right? Okay. So if you see here, you have class stuff in a gray block. So basically, if we have a syntactically and semantically correct program, we will try to convert it back. But for the pieces of code that we don't know how to compile into blocks, we're just going to have a gray block for that lexical construct. So there are programs that we simply can't represent in blocks. So sometimes we will fail.
Yeah, and you think about the student learning. He's learning classes, so he's beyond what the block paradigm supports.
Yeah.
But there are definitely kids who are switching between the two. One thing that we've added to help discovery is the same paradigm that we have in blocks, which we call the toolbox. So you can, for example, drag. It's really a documentation and also a snippet. You can drag a snippet. If you know the API in block, you can now drag it and have the JavaScript equivalent. So if you're wondering how you do loops in JavaScript, which you are when you're learning to code, you drop your for loop and put it there, and it's at the same place where you would actually go and look for the block as well. All right.
Can I have one more question? It's Artyom, Northeastern University, Boston. So I'm curious about your static TypeScript dialect, how compatible or incompatible it's with the existing TypeScript code base. So, for example, did you have, when you wrote your thing, did you have to compile some TypeScript libraries with it to use them in the code? I don't know.
Yeah, so we didn't.
You want to take over the screen, Mikhail, or?
No, I think it's fine. We didn't really compile any libraries. The main reason is because, you have 16 kilobytes of RAM, and there is pretty much no real-world TypeScript library that will run in that.
Mm-hmm.
I think we did take some, but that require. Usually you just have to do something with them manually anyway, because they are just not written for this kind of restricted environments.
Mm-hmm.
So so we didn't really try to compile an existing code. Lots of features of TypeScript are supported, but I'm pretty sure you would run into quite a bit if you try to compile more of the existing code.
I see. Cool. Thank you.
Okay, Pele, you want to do GitHub now?
Yeah, let's do GitHub. All right, so
it's time for GitHub.
Yeah, let's go back to blocks, which is kind of our.
And maybe also talk about extensions, and those two sort of go together because that's a great feature.
Right. So I'll actually create an extension out of this kind of. So one way to store your code, as I was mentioning in MakeCode, is to save to a file, which is kind of the thing that works in all the schools. But we did a lot of work to bring GitHub to the classroom. So I clicked on this little button here. So I'm here, and I made some change. Let's say I switch on off, and now you can see that there is, oops, wrong icon. Let's go back to, there is this icon here, and it's telling me there's something to push up. There's this little up arrow. So we tried to use some of the iconography of GitHub and the ideas. And then when I'm doing blocks, we can't really show a diff like it would show in text because we don't think kids really get it. But what we show here is the idea is that everything that's gray, like very shallow, is not modified, and anything that has the actual colors is something you should review because we made some changes here. So apparently we messed up. We added a console log here, we added some class, and we made a whole bunch of modification here. And if I'm happy with those changes, I can just say, added some logging for Tom, and I can click commit and push. And we do commit and push, so we don't really run a Git locally. We really try to encourage students to push immediately to the browser so that they don't lose their work, because they might just change browser, change machine, everything gets deleted. It's really important to get them to do the code. So that's the block experience. I'm going to redo a change. I got my upload here. I got my diff that comes in. And if I'm not happy with that, I can revert it. So I can revert that. I'm going to do a change because I need a few commits. We can revert changes that haven't been committed. So that's pretty easy, but also it's possible to review the whole history of a project. So I can see that today I've done 6 commits, and I can go and take a look at this one. It's like, this was my favorite version. So we can restore that particular commit by copying the tree at the top of head, and that keeps the history and also allows to do a very efficient undo of any changes in history that you've had. So it's a very nice feature for educators. We've done also work, of course, on the JavaScript side. So if I'm making changes here or, adding some files, let's say that, then if I do my diff, we get the typical text-based diff that you would have, and I can also push my changes. And all of this is backed up in GitHub. We have fairly good collaboration in the text-based editor where we can merge changes in the browser. So if you have multiple students working on the same code, we'll also have a merge UI and so forth. And that is, in a nutshell, we can go to GitHub. So that's, although I don't know. Oh yeah, the iframe is not allowed to pop out. This is my little demo engine here. Cool. Then there's the extension zone. So the way you extend MakeCode, there's only so many blocks we're going to put in here, is we create extensions. So let me go back to my demo. And what I'm going to do is I click on the wrong button. I'm going to click on Advanced, scroll down, and there's this extension here at the bottom. And now you can see either extensions that we have built in the system, like pixel animation extension, or you actually have extensions that are actually hosted in GitHub by a third-party company or by a developer or something like that. So for example, not so long ago, I create an extension, and you will see that. I'll go into a different browser, but it is a GitHub repo. Ooh, and it's got all the files that I'll need. And what I can do with that is I can import it. So I can just click on that. It is going to add that into my list of dependencies. You can see that now I have my arcade sprite data that is loaded. It's got all my files that I've added. And I've also got somewhere, I think it's under sprites, a set of new blocks. I'm going to go back to blocks just for the kick of it. I think I'm adding sprites around here. Data. Okay, so these are new blocks that I've added as part of my extension. So we can, so we have an ecosystem of extension that is built out of TypeScript that is hosted in GitHub, allows people to publish things under name, version it, and so forth. It is now very easy to build because we have an excellent GitHub integration that allows people to write the extension directly in MakeCode and test them in the editor. So that's kind of the end-to-end story, Tom. I think I've talked for a long time.
Yeah, well, I think we've covered a lot there. We've got 10 more minutes. Do people have any other questions? You can type them in the chat, or you can unmute, because we just have about 20 some odd people on, so I think we can handle if people want to ask questions just using audio.
I guess it's also worth to mention that we are open for collaborations. So if people, are interested in working with us, building their own editors, collaborating on existing ones, extensions, education, research, and so forth, we're open for that.
Yeah, absolutely. Lots of good opportunities. Okay, well,
Hi.
no, yeah, okay, please go ahead. Just say who you are.
Julia, Northeastern University. Thanks for the great talk. So I wonder, do you have any support for collaborative work for students? Like, could they make a game together somehow, just maybe via this GitHub?
So you're, so I mean, collaborative editing environments where you're actually seeing the cursor, like Google Docs or things like that, we don't have, but you can Peli has some things maybe to show. Obviously, we have, you can, right now the main way to do it is through GitHub, but you have to, it's not, it's asynchronous, right? You're not seeing the edits in real time.
Yeah, I'm gonna make a conflicting edit just to show that. Yeah, as Tom said, we don't have anything real time, but we do have a fairly good integration for GitHub. So now what you're seeing is I made a change.
But you are showing your entire screen. So
yeah, Peli, we're seeing your very wide screen. So
oh.
It's very hard to, yeah, there we go. Oh.
No, I need to unshare and reshare.
Okay. So you're going to show how we handle merge complex. Yeah, okay.
Yeah, so the experience is you're coding in your you're coding on your browser, and this is very similar to what happens when we're developing. We get notified that there's some changes that are pending, so we're behind from what the cloud has. And what we can do is basically pull the change, which is going to also merge them. But no, I don't have a conflict. Okay, so we did a three-way merge, and then we're back into happiness. So okay, so I'm going to make a change here. I'm going to do 12, and then I'm also going to go and make a conflicting change here into my demo.
You can just delete the line, right?
Oh yeah, I guess. I'm not. I lost the line. I lost the line. All right. Okay, so committing that. So it's committed, and now changes. Cool. I'm gonna grab them, and now it's basically we have a merge conflict UI here. You can see that here. So I can keep the local copy, I can keep the remote copy, or I can keep both and then edit them. So if I say, no, I really want to keep my color, I'm just going to do keep local, and now I'm ready to push my changes. So we have a very basic support for collaboration out of master for students. They could also do branches.
And Peli, we're changing, GitHub's changing that name to main, as I understand.
And yeah, there's been talks about changing the name, which is going to be a fun, exercise. But we'll do it if we have to, for sure.
Good thing.
Yeah, so blocks is a bit more tricky because we don't have really a great merge story for blocks. Right now, so this is still up for grabs as far as research. I think there's one product, it's probably one editor out there that does it, but there's really no, how do you convey to a student who's basically learning that these blocks are conflicting with his friend's block, and how do you avoid that? do you even do conflict resolution there, or do you just dump all the code in the workspace? You know, you could, for example, disable some blocks or things like that. So yeah, we don't really have an answer on as we can merge the blocks by going and doing a merge in JavaScript and then go back to blocks. That's the way we do it right now.
Thanks, Pelly.
Yeah.
Thanks. And do you think it would be useful to have some distributed collaboration, or is it too hard to do? Or maybe that there is no.
I think this is a great research question as far as, you know, do you need to be live coding to learn? Do you learn better if you're live coding, or is it better async? I don't think we have an answer on that.
There's some evidence that research that peer programming, I mean, has some, and working with your peers definitely has some benefits. There's a live code or live share experience that VS Code has done. And in that case, I think you share just like a directory. Yeah, we don't have any plans right now on the books for sort of live share. But there is some infrastructure at Microsoft. Maybe someday we'll be able to make use of it. It's an interesting question.
It's unlike a Google Docs, because we're, you know, whole program compiled. If you have a slightest typo in any of the files, you can't use your program. So we don't know whether that would really work.
Right. Yeah. So we do not have plans. I'm just saying. Yeah, I'm sorry. We do not have plans for live share or anything. There are groups. There is a live share option in VS Code, but this isn't VS Code. This is in the browser.
Yeah, it's worth mentioning that the Microsoft, so the Microbit has built a product called Microbit Classroom.
Oh, that's a good point.
And they built that around the editor, because the editor can be used as a widget. And that allows a teacher to create a classroom on the spot and push the code to every student, and also see the code of every individual student and collect that. And you can check it out. It is classroom.microbit.org. It is not real-time collaboration. It is more a traditional teacher pushes an exercise to all the students do it, they recover the assignment back, and I think there is like the student and then the classroom. But yeah, there's a whole joining mechanism going on for the classroom. So you create a classroom, then the kids have to enter the emojis and the code, and then they're in. Yeah, but that's that part of the cloud we didn't build. That's built by the Microbit Foundation.
Thanks, Pelly. We've got just 3 more minutes. Probably time for one more question. Any other questions?
So the question about plans was more general. How do you?
Oh, okay. Well, what are our plans? Yeah. I see your point. What is the future? What are the future plans for MakeCode? So we've actually acquired some funding to do what we would to do a new effort, which we're sort of thinking of more as direct to consumer. Most of our use of MakeCode is in the classroom. And about a year ago, we started thinking, well, maybe we can do something more self-guided that is just direct to the student. You know, whether the student's at home, you know, on the bus, it's an after-school activity, and also based on arcades, so that it would be something which we wouldn't go through a partner like the Microbit for. So that is actually just started up, and that's a different sort of effort, because like with the Microbit or other things like Minecraft Education Edition, really we have a partner who's selling to a school or to a state, country, you know, end to end, the hardware, and we're just part of that software. So that's something that we're just ramping up right now. But that's sort of to complement sort of our in-classroom use, to have more of a direct to student approach, wherever that student might be. So we don't have a lot to say about that, about what it's going to look like, but that's sort of the general direction we're heading. Okay, well, we've got just a minute left. So I'd like to just take the time to thank you all for joining. I really appreciate you taking time out of your busy day and learning more about MakeCode. Definitely, if you have questions, feel free to mail us. I think our emails are all easily discovered. I'm tball@microsoft.com. If you have other questions, feel free to mail me. We thank you again for joining. It's 1 o'clock, so we're gonna stop this conference and let you get on with your day. Thanks again.
Thank you.
Bye bye, everybody.
Thank you, everybody. Thank you.
Bye bye.